Hello. During this lecture, we will discuss different forms of regression models. So far, you are already familiar with linear regression model. So if we analyze the relationship between y and let's say x1, then according to this linear regression model, the rate of change of y is constant. So if x1 is represented by a linear term, so we just take the variable as it is and we put it to the regression model, then we automatically assume that dependency of y on the value of x, in our case x1, is constant. It does not depend on the value of x. Probably it's hard to understand what I mean at this point, but at the end of this lecture, you will understand how different forms of regression models actually depend on our assumption regarding the relationship between x and y. I mean, independent and dependent variable. So, of course, there are many alternatives. But since during this course we concentrate mostly on OLS and in general in models which are linear in parameters, here you can find a very short list of alternatives. Models which are linear in parameters but not linear in variables. So log-log, lin-log and log-lin models generally include logarithm as dependent or independent variable, or both, as we are going to discuss. When it comes to reciprocal models and logarithmic reciprocal models, I have to say they're relatively rare, so probably you will not have to deal with this kind of models. But if you can come up with any good examples and you can present an example of such a regression, of course you can get additional points, as announced at the beginning of this lecture. And finally, polynomial models. So when it comes to polynomial models, they are relatively more popular. Like, there are many applications. You can find numerous pieces of economic theory which would support the use of polynomial model. So we will start with log-log, lin-log and log-lin models. And before we do, I would like to discuss very briefly the properties of the natural logarithm. So those are the formulas you might need for mathematical form of regression model transformation, because this is what you start with. Usually you begin with some formula, not always however, but for many well-established economic models this is how it works. You will see this in a second when we discuss logarithmic models. And using those formulas you can actually transform multiplicative model to logarithmic model. So in this case, your task will be much simpler when you specify the regression model. So logarithmizing or taking the natural logarithm of data is frequently used to fix non-normal distribution. You do not know this at this point, but actually logarithmizing can help to fix heteroscedasticity. Because one of the reasons behind heteroscedasticity is asymmetrically distributed data, skewed to the right or to the left. And in general, logarithmizing can be used to smooth the data, which means making difference between the values in different groups less noticeable. So, for instance, if you analyze the determinants of economic growth, or let's say GDP per capita, for a really big set of data, when you include many countries with different level of income, it would be better to logarithmize, because obviously we have several distinguishable groups according to the level of income. So in order to illustrate what I mean, I will demonstrate to you how logarithmizing can help to fix non-normal distribution. So for this purpose, we will use international trade dataset attached to this lecture and Gretel. So I already did it myself, but I would like to show you how you can do this step by step. So you have to highlight the variable, add logs of selected variables. So log actually stands for natural logarithm. I know that this notation might be a bit misleading, as many students ask if you have ln for natural logarithm, why it's denoted as log, and the answer is because I don't know, but this is natural logarithm. So now we can analyze the frequency and normality. So first I will start with unadjusted variable. As usual, frequency distribution, test against normal distribution, and let's have 50 beans. Again, so as you can see, the data is not distributed normally. So this one stands for GDP, for the product of GDPs of Poland and trading partners in different years. In the next video, I will explain every variable in this data set, but at this point, I just want to demonstrate how taking the natural log can help to fix non-normal distribution. So again, when we take just GDP product, it's not normal, definitely, based on visual assessment and the result of Jark-Berra test. And now, when we analyze frequency distribution of the natural logarithm of GDP, my bad, I actually did not add test against normal distribution. So here we are. So still, this distribution does not look like a normal one. I mean, perfect normal distribution. But based on the results of Jark-Berra statistics, you can definitely see that p-value is bigger than 0.05, significantly bigger. That's why we cannot reject zero hypothesis about normal distribution of the variable. So that's how taking natural logarithm of the variable can help you to fix non-normal distribution. And since non-normal distribution is one of the reasons, I would like to underline one of the possible reasons behind heteroscedasticity problem in your regression model, sometimes taking natural logs can help to fix heteroscedasticity, but not always. Okay, so that was it when it comes to introduction. In the next video, I'm going to cover log-log, lin-log, and log-lin models, and I really hope you enjoyed this one.